Thanks, Justin. It's good to be here. I've watched many of these little webinars, and I find they're always rather fun. So today's talk's going to be a little bit different, probably than those you're used to. Generally, as scientists, we are often guilty of the whole, I have a method, I have a data set, I have an objective, I will deliver on said approach, and I will show my results and why they're of impact to the scientific community. And then, we all live in this little bubble that we appreciate our own results, and then the world at large kind of moves on. So what we're going to do today is we're going to play a little more from on the human side of things. And note that the things that the public tends to latch onto are those that they can interpret directly, and oftentimes science can generate some very salient products this way, if a little indirectly. So anyway, moving on, we're going to be. Oh, apparently there we go. Great. So quite unlike a typical scientific approach, we'll start. I would like to actually encourage you guys to think about this talk, not in terms of necessarily science, but in terms of what sounds and your own sensors mean to you. So, for instance, we all are fully aware that there's some sounds that we hate and some sounds that we like. But it's actually a fairly open question as to exactly why that's the case. For example, what makes a sound interesting? If you stop and stop and sit there for a moment and consciously analyze all the things you're hearing, why are some interesting and why are some not? What's in the background? What's in the foreground? Why is a sound horrible and another sound is pleasant? Why is musical interesting? For example, every culture in the world has a universal sort of appreciation for music, but there's some types of music that we simply can't stand, and others find absolutely delightful. And then some things are acquired. There's some things that at first you think sound bad, and then after a while you kind of like them. So what's personal? What's evolutionary? What's acquired? And more importantly, to us, what does an interesting sound, look like? Since we hear sounds, but we don't necessarily look at sounds very often, at least from an appreciative perspective. So this is actually a little quiz that I found online, which is a first grader quiz. Circle the thing that's pleasant or not pleasant. Is it noisy or good? So you have various examples of things that we'll recognize. There's sure some diversity in the answers, but when you stop and think about, there's quite a bit of interesting science and math behind all of these things. We're inherently trained neural nets, and so we have some appreciation that's built into our little brains. And so in that sense, we as scientists view the world through sort of a sensory extension, and even not scientists. We are tools. We design tools. We have an impressive battery of sensors of our own that are built in. But at the same time, we also recognize that those sensors are inadequate. And so, our interpretive capabilities are based on our personal bandwidth. So, for example, this image on the right here is literally a numerical model of the ear and its sensitivity to various sounds. So our ear is quite an extraordinary little device, but it is still limited. So we can only hear at the upper limits or lower and upper limits from 20 to roughly 20,000 hertz in terms of sounds. But obviously there are many other bandwidths out there that are very interesting, both physically and phenomenologically, that we cannot directly access. So we have to transpose them somehow. We also have, for example, this Lindsay's acoustic wheel, which shows the various kind of bandwidths and physical phenomenologies that are of relevance to different fields. And it's often good to remember that a lot of those overlap and can be transposed from one field to another. Another example of a neat tool that operates on bandwidths well outside of our sensory sensitivities is, for example, this INSAR image, which shows extremely long wavelength deformations, which otherwise would just go cleanly beyond our perception. So lastly, is this example here, where any time series, be it acoustic or seismic or anything else, can be represented mathematically with a combination of the summation of sine waves of different phases. And so this is the one that obviously as seismologists we use the most, and so we'll be treating mostly with today. So this image on the right here is in particular what we'll be seeing a lot of, and it's called a spectrogram, where you can take an original input time series signal like this wiggle here, decompose it into its various frequency components, and then view the amplitudes of those different frequencies inherent in the original time series as this sort of image as a function of time. So in other words, you have frequency content as a function of time, and this is called the spectrogram. And so the warm colors here show that you have the prominence of certain frequencies, whereas the darker colors show that those frequencies at that particular time in your signal do not really contribute much. So on the other hand, a lot of what we do here with our impressive tools, which are extensions of our sensors, we generate these results that then have to be forced back into our own sensory range so we can interpret them. So for example, the spectrogram is an excellent example, right? We can't hear some of these frequencies, but we can sure see them when we transpose them back to a spectrogram. The arts, for example, have been doing this for millennia, right? So their whole gig is to take some kind of phenomenon and interpret it in a different way that we can appreciate, at least universally. This is an example very quickly of what we sort of can do with in terms of transposing things back to our original bandwidth. So this video here is one online. It's credited to Michelle Wereth-Mueller. Basically it's a seismic signal, right? Or an acoustic signal. In this case, I think it's hydrophones off the west coast of Canada. And basically they're just recording fin whale sounds. So fin whales will communicate to each other by these pings and bloops. And if you visualize the data, so this is 5 minutes of continuous acoustic data visualized in 0 to 50 hertz. And if you visualize it like a spectrogram, you'll see that there's these ping sounds here. And those are basically the whale communications. And obviously in the 0 to 50 hertz bandwidth, we can barely maybe hear that. So what we can do is we can just speed up the signal, right? So we say, okay, well, let's speed it up a factor of 10. And now suddenly this frequency range is not 0 to 50, but it's 0 to 500. And since we've sped it up a factor of 10, this is now no longer 5 minutes, but it's roughly 30 seconds or so. So what it looks like, as I just speed this up a bit, I guess it won't let me within the Zoom platform. But as you'll see, as we're playing the sound, right, you have the various pings that happen for the whales. This background here is a sort of microseismic activity, right? Just constantly just buzzing with low frequency sounds. But the fin whale sounds come out as these sort of relatively broadbandish peaks, but very sort of distinct in time. And so this is a character that we'll be looking more at, the sort of time sparsity, but frequency broadness. Yes, moving on. So let's develop a bit of intuition related to spectrograms. And so these are 3 different examples of spectrograms created from real data, so real time series data. And we're going to try to guess the sort of corresponding acoustic or seismic or whatever signature that was responsible for it. So this top left panel first, we can see that our frequency range is quite low, right? It's 0 to 20 hertz. Our time scale is reasonably long, so 600 seconds or so, 660. And you can see that you have this background buzzing sound. This low frequency background buzz, right? And so that's the microseism in this case. So these are seismic frequencies. And you'll notice that you have these sort of very sort of time sparse again, but frequency broad sort of pings that happen. And so a lot of you will obviously guess immediately that this is seismic data because of the frequency range and so on. And it is indeed a large ice quake on Erebus volcano. So Erebus has some 500,000 a year of these at least. We haven't an actual estimate, but it's a lot every year. This center one, a little more tricky, right? So we have a very short time period, so 3 seconds. and a very high frequency range. So this is 100 hertz, this is 10,000 hertz. So you can say, okay, well, this is 100 to 10,000. It's well within the human audible range. So it's basically sound in this case. And these patterns are quite different, as you might note, than this seismic pattern here. You'll notice that we have these bands that are very frequency sparse. So in other words, very limited and very distinct in frequency, since the warm colors are higher amplitudes. And they are time sort of prolonged. So in other words, these are tones, right? And these little blips here are basically harmonics of that tone. So keep in mind that we're in a logarithmic scale. And so you might imagine, okay, well, this could be maybe an instrument, maybe something like that, right? These are basically tones that glide around smoothly. Unclear what they are, except that I happen to know, and it's Beyonce singing, the national anthem. So, so these are, you can see this as, oh, say, can you see, kind of deal, and so these sort of patterns are very, especially if you have a nice voice and can pull it off. Otherwise, it's probably a little more garbled looking. But it's basically these harmonic glide patterns that are very characteristic of human vocal tracts and instrument tracts, where the higher harmonics sort of decay as a sort of an exponential amplitude with respect to the bass harmonic or the bass note. So this third one on the right, this is a little more tricky because obviously the frequency range is seismic, or at least what we'd expect from seismics. The time scale is 15 days. So this is very, very long by comparison to this 3-second burst here. So this is probably not a human speaking, right? But at the same time, it shares a lot of characteristics with the human speaking, and much less so with the distinct little ping of an event. So you can see this is probably not a little localized transient event, but actually has some very sparse spectral signatures to it. And this particular type of signal is what we'll be dealing with largely today in terms of at least the science of it, and we'll be going a bit in that. And this actually winds up being a recording from an ambient seismic recording. This one is a waste divide. But such recordings, with sort of arbitrary patterns like this, have actually been shown to occur pretty much everywhere in Antarctica, so long as the station is on ice and snow, and in particular firn, which we'll be getting to in a bit. So what this actually is something that Stephen Colbert coined as ice ghosts. So it had its viral moment, its viral 5 minutes of fame, as it were. And the reason for that is because I made sonifications of these things, and they sound truly weird. So we'll be going into that a little bit. So first off, let's get some science out of the way related to that spectrogram. And this is this is where the interesting, where we usually find our comfort zone. We have our computers and our data, and we crunch massive amounts of data and find some kind of physical insight. And this is essentially what happened. So there's a series of now 4 papers on this subject, which have been published over the last couple of years, related to the nature of firn. So as a field, cryoseismology is in its infancy. So we're just starting out. It's really brand new field. And so the way that this seismic firn, which is the transition from loose snow on the surface to solid ice at depth, the way that this seismic firn affects seismic waves is actually quite exotic. So it's a very, very low density medium at the surface and very high porosity. It's up to 90% air. And then it very rapidly transitions to solid ice, which has a much higher density, all within, a few tens of meters. So firn profiles in Antarctica act as sort of these extremely severe micro basins, where you have these massive gradients in parameters, and so they tend to trap waves in bizarre ways. And so, where we as seismologists, we like things to be nice and smooth and so on, that we don't usually address extremely high parameter contrasts and figure out what they do to our wave fields. But in firn, we have to, because the real way that we have to look at firn, I'm going to move myself, there we go, is not this smooth profile you see on the left here, on the upper left panel, A. This is usually what we like to think firn looks like in terms of parameter variations with depth, but it's actually more like this black line here on the right, panel B, where really it's sort of peppered with these air layers and these ice layers and all sorts of things that cause massive swings in parameters. And so you get these huge parameter contrasts that then are responsible for all sorts of bizarre wave field effects. And since Antarctica is really quite largely covered with ice and snow, we wind up with having this sort of pervasive wave field effects all over Antarctica if we just plop down a seismometer and listen. So this is Rick Astor down on the left here. Many of you know him. He was largely responsible for putting out this huge array on the Ross Ice Shelf, some of which some of that data we'll be seeing today. But yes, Fern causes bizarre wave field effects. And so as a few examples, we'll be seeing results from a couple of arrays today. So for example, the time array, which is this one at Waste Divide, which is this little circular array that they were using to test shots. And I just kind of ran away with their data and then decided to publish a paper on it all sneaky like. I'm joking, they're on the paper too. And then of course the larger Ross Ice Shelf array. And all these stations, regardless of where they are, demonstrated patterns of these resonance peaks. And what they look like are these things. So these are, for example, 3-component spectrograms. So, radial, transverse, vertical. And you notice that there's these sorts of peaks that just kind of shift around. And sometimes harmonics of those peaks emerge very temporarily for some reason. And then they go away, the pattern shifts away, and then it comes back and does something else later. And this is, for example, 2 years of that data on the Ross Ice Shelf. So you can see that there's a whole lot of activity going on. These peaks sort of wander around at random, and yet there's these underlying long-term trends to it, and then these very short-term trends to them, and there's all sorts of interesting chaos to look at. So when we first started analyzing these, honestly, a bit by accident, because we were initially trying to do crustal structure stuff with them, we just we stumbled on these things and we're like, these are not normal seismic signals by any stretch of the imagination. We figured at first maybe they were instrument resonances. They aren't, because they map across all sorts of different instrument types and deployments, and surface expressions or not, or it doesn't matter, they're there. And so and they react very strongly to environmental forcing, as we'll see. So particularly windstorms, depositions, snowform interactions, things like that. So there's this really strange coupling effect between the wind at the surface, because they are wind driven, and how wind couples to the surface and the structure at the same time. So there's both source variation effects and also structural variation effects, as we'll see in a second here. So for example, here's a few examples of how you can track these resonance peaks over time. With respect to different atmospheric forcing. So this is on the left here. These two here are basically the impact of passing storms, for instance. So these big bright spots, which are this triple storm event that's in this black box here on the surface. So these dots, by the way, are just the tracked spectral peaks. So we just find the peaks of these spectra and we track them over different components, so north and east components. And you can see that there's these features. For example, a storm will pass sometimes and completely mess around with the pattern. So the peaks were down at 7 or 8 hertz on this bottom left panel here, and then a storm passes and suddenly it's up at 10 hertz, and then another storm passes and then it loses hertz or something, and during the storm it goes haywire. And so there's all these interesting jumping from one stable or semi-stable mode to another. And if you look on longer timescales, after a storm passes, you also get these longer sort of 10 to 30 day decay patterns that happen. And so there's clearly something where the storm rearranges surface snowforms. Those snowforms get eroded. Another storm comes along, messes with it again. Everything changes again. So there's clearly a source coupling effect with the wind and the surface. So that's what these triple storms here are about. Also, there's a very high sensitivity to surface air temperatures. So if you have, so we tracked this big melt event in 2016 that spanned almost the entire Ross Ice Shelf, and we wanted to see what the impact was on the various, fern songs here. And in this black box is when the melt hits, or at least the warmer air temperatures hit. And it lasts about 12 days or something. And you can see in this region that if you track those peaks across all stations, you have this sort of decay and quieting of the pattern. And as soon as you have a return to colder temperatures, then the pattern tends to return. And so we can actually model this physically to an extent. Even if there was no actual surface melt, so long as your temperatures approach melting, you can actually weaken your snow by up to 40% in terms of elastic moduli. So you can model the penetration of that anomaly with depth using a diffusion sort of approximation to it. So you can get a depth to which these things will penetrate, and that should affect some frequencies more prominently, since the higher frequencies are probably more sensitive to surface. But again, the physics of these sources of these this phenomenology is not exactly constrained. We have ideas and some that are supported by data, but we need something much more dense and robust in order to analyze how they work. Another thing that these spectral peaks can tell us is actually anisotropy, and that's a very tricky metric to get in a medium like snow and ice. And the reason for that is that anisotropy in flowing ice and snow is actually depth dependent. So ice is a particularly bizarre medium where it might incur some weaknesses, somewhere upstream when you flow, and then the flow will get rotated, but those weaknesses will remain, so they'll get advected. So you have strange fractures and crevasses in all sorts of directions. Those are buried. And deeper on, you have other phenomenology like crystal axis alignment, which will affect your anisotropy in different ways. And then you have the firn on top of it, which doesn't behave at all like ice. It's completely different. And so what you can do is you can track these different peaks on your horizontal components, and without doing anything, you'll notice that often they split. So you can see these blue and red circles here on the right. And you'll show that basically there's an offset between your two horizontal components, and that's pretty persistent. But it changes as a function of frequency. So down here, you can see the red one roughly comes first. And then down here, higher frequencies, the blue one comes first. And so there's actually switches in the axes of which peak arrives first on which component. And you can track that. So I designed an algorithm to track all these peaks and rotate them within their ideal particle motions to figure out what the axes were. And then you can actually sort of map those to directions, of fast, slow directions. So luckily for that array at Thwaites, or at Waste Divide rather, we actually had access to a direct active source in a perfectly mapped circle. So as a result, we were able to directly see from shot gathers which directions were fast and which directions were slow. And when compared with the inferences from resonance peak splitting, as I showed you just before there, you'll notice that the directions map pretty similarly, with a bit of extra noise, because of course this is not an exact science and my algorithm is probably terrible, and so on and so on. So at the time array, we were able to validate that these measurements carried the same information. For the Ross ice shelf, of course, we had no active sources, but what we did have was very nice overhead imagery and some papers that had meticulously documented all these advected crevasses and so on and so on. And so we were able to take a dense portion of the array at the RIS and basically map and see what the fast and slow directions were as a function of frequency. And as such, these red little bars here denote where the directions, where the fast direction wants to be at higher frequencies, or is that black? Oh no, yeah, red is low frequencies, black is high frequencies. And so this is essentially the direction of flow at higher frequencies affects the fast direction, whereas at low frequencies it doesn't. And so essentially what this means is that at low frequencies, you're largely sensitive to large crevassing systems. So you have these, if the flow is in this direction, you get these big open, these crevasses that form perpendicular to an accelerating flow because it's an ice shelf. Whereas at very high frequencies, you don't see that because you're only sensitive to very local near surface structure. So what you're largely sensitive to is the firn, and the firn is not ice. It does not fracture like ice. Instead, what it does is it stretches like a plastic foam. And so you have an inherent pore space in snow, and you slowly stretch that that snow fort, and it, heals itself as it goes and stretches along like a foam. And then you end up with one direction that has a pore space that's aligned with flow, that has much lower what we call tortuosity. So if a wave travels along the pore space that's stretched, it is faster than the one that travels against it. And so you get this bizarre sort of anisotropy, which is fast along the direction of flow, which actually breaks a lot of conventional wisdom on the subject. So anyway, this was a lot of science, and this is 4 papers worth. And if you guys want to see what they're all about, I'll put some links at the end of it. But essentially, this was an introduction as to why these resonance features on ice shelves are interesting. But not from a human perspective, right? These are the scientific results that you publish and you feel good about and all that, but that the public will largely just kind of ignore, which is life, right? But there are other ways to view, as it turns out, how to view this data and make it more socially relevant, or at least more socially captivating. So for instance, when we first saw those spectrograms, they look awfully human in some ways. They have spectrally sparse patterns, but very time persistent patterns. So it's kind of like a bit of a song. They're not perfectly harmonic, except when they are, right? So they're sometimes harmonic, but they might sound like something interesting, and we like interesting. So what we can do with when we talk about sonifying signals, typically it means we simply accelerate them. So if we have a signal that has a length of 10, or there's say a length of 10 days, and we decide to increase it by a factor of 10 to transpose the frequency range, then we get a signal that is 1 day long that we can listen to. The problem with that is, as you've seen from these previous results, is we have years of data. And so transposing 0 to 50 hertz into, 0 to 5,000 hertz is still only an acceleration factor of 100. And so that's still a very, very, very long signal to listen to. And, it's maybe not really suitable. So how do you then go further? If you're willing to lose a bit of temporally varying information, but you want a reconstruction that is still frequency, reliable, or at least representative of what your original signal looked like, well, then you have to go into a little more detail. And so we'll see a few of those algorithms today and some of the assumptions that are inherent in them. You want to preserve mostly the qualitative frequency content, but transpose it into the range that you want while compressing your time axis to what you want. Then of course, on top of that, you can go much more egregious. You can do an interpretive way of looking at things, which is to say you listen to your seismic data, or you look at your seismic data, and then you just sort of map it to whatever your brain feels like mapping it to. So for example, this is simple acceleration. So Zhigang Peng does quite a bit of this, and so he likes mapping earthquakes. And so this is, for example, his process of doing so. You accelerate that, you get these various pings like we've listened to in the fin whale sort of situation. This second one here is an instrumental transposition here, where you learn some kind of a map between a seismic signal sound and instruments of an arbitrary nature. So for example, this is a learning algorithm. So you train it on saying, okay, well, this maps to this, this maps to this, this maps to this, and then you input a seismic signal and it plays you a song, right? It's kind of a neat form of advance, and people like that. And then the third one is completely unrelated to the actual data, but you just take, for example, the frequency of earthquake occurrence and map that to a sort of instrumental group, and so you create a symphony based on the level of activity of medium, for example. So a lot of completely arbitrary ways to do this. Now, in our case, we would like to maintain the reliability or the truthness of our signal. So one thing I would like you guys to think about is what things sound good to you and what don't, and how they look. So for example, we have a spectrum that looks like this. What might this sound like? So this is a nice little YouTube video that I found about it, that play different harmonics or different tones and show you what those tones look like. Okay. Much of an intro, right? So this is the same tone, but it's different instruments playing them. So for instance, this is a piano, and you can see the corresponding shape of the spectral peaks. They're near it. This is, I think, a harpsichord. Yeah, harpsichord. So obviously you get these sort of tremors in your peaks. That's a nylon guitar. So the shape of the peaks matter. Obviously you see that all these little harmonics decay at different rates. So that was a sitar, which bass harmonic was low. Viola, which I cannot stand. Cello, many more harmonics. Baritone sax. So I think the point has been made. And the point for this is some of these sound better to some of you than others. But visually speaking, there's quite stark differences between the same tone played on different instruments. And so when transforming this sort of spectrum into something you want to listen to, oftentimes these peaks will have a variety of noise and other built-in artifacts and so on. And so obviously you want to contain, you would like to be able to play this, whatever this pattern is, which is 2 years of seismic data, transpose it to a frequency range that you find interesting, maybe 0 to say 5,000 hertz. And at the same time, you would like to be able to compress this 2-year time axis down to a soundbite that can be played and listened to in sort of an appreciable way. In other words, maybe a couple minutes rather than have to sit there for 6 months and listen to it. So that brings us to ask questions on why ice ghosts are so compelling. It's because they're mysterious, right? Their spectral content looks human-like. They're both dissonant and consonant. They're persistent, and their context, particularly in the context of climate change, evokes the idea of a sort of a hidden message, like almost as the ice shelf is trying to tell you something. And in some ways, it kind of is. As we've seen, those spectral peaks contain a massive amount of information that we can mine. And so, but really, in truth, they're just plainly strange, and we happen to like strange. And in particular, we like to find patterns in things. It's how we've evolved. We're very good at finding patterns, often to a fault, in the sense that we will interpret as causality what is in fact coincidence, so correlation. But we love patterns, and these ice ghost spectral peaks are patterns at their best. So. So let's look a bit in terms of classical limits of compression, as I mentioned before. You would like to take a spectrogram like this and compress it by an arbitrary amount, n, but also extend the frequency range by a different amount, m. And so extremely long data runs into the too long didn't listen problem, right? You don't want to have to listen to 6 months of data. And so representative sound bites that map the original frequency scale or to something of interest while compressing correctly are rather difficult things to do. And so one of the things that we think about when we look at a spectrogram like this, incidentally, is that the spectrogram only carries magnitude information. So it doesn't tell you how the different frequencies line up to reconstruct your original signal. So if you start doing things like compressing your time axis arbitrarily while also trying to map it to an arbitrary frequency range, you run into problems. And it's because when you look at a spectrogram, if you're trying to rebuild your original signal from it, you also need the phase component. You need to know how things line up. And so this is a fun example that I found online that I actually played with back in the day, is if you take the magnitude and the phase of one image and you swap them and then do the inverse Fourier transform, what you'll find is that the phase actually reconstructs the vast majority of the actual image information. And so when we look at images like this spectrogram on the right, this is interpretable to us because it makes sense. A phase image like this wouldn't make sense at all because everything is just mapped between minus pi and pi in terms of phase shift. And so it just looks like noise, like we can't really see anything in it. Each frequency component has its own completely arbitrary phase shift, and so there's no coherence to it. And we, as I said, we like patterns, and it doesn't look like it has any patterns. So from So our job, of course, is that we would like to go from something like this on the right and reconstruct a time series that sounds like something we like. So how do we do this? Well, we have to reconstruct the phase from the magnitude only. And there are many strategies for this, one of which, and the most basic, is a minimum phase reconstruction. And this basically is an iterative process that basically starts with, a known magnitude, mn here, in the frequency domain, and an unknown phase, phi 0, which, or theta 0, which we just guess. So we guess a phase with a known magnitude. We take the inverse Fourier transform. We recreate, that gives us a time series. On that time series, we impose causality. In other words, things can't happen before 0. And then we take the Fourier transform. That gives us a new magnitude and a new phase. And then we say that we in fact know the magnitude. So we replace this new magnitude with the one that we know is true, and we just repeat the process. And as it turns out, this will converge towards something that reconstructs a phase that looks a lot like your original signal. So this is one example where we enforce a known magnitude, and this is in fact enforcing causality. So through the Hilbert transform, this winds up being the removal of all negative frequency components, for those of you who are interested in such things. Another extension to that, though, is that only works for one Fourier transform at a time. An extension to this is called the Griffin-Lim reconstruction. Oh, it's Lim, actually, not Lin. And all we know is this, for example, a spectrogram. So here on the bottom left, I have this chirp. It's basically, well, it's MATLAB's splat function. If you load it, it's a sound. And it's a spectrogram that basically, sounds like pew splat, and so the time series is the real time series is this blue thing that's in the background, which I'll show you. And what you're doing here is you're not imposing causality. What you're doing is you're imposing consistency in the way that the magnitude varies over time. So you're using the actual bins of the spectrogram Fourier transform, the short time window Fourier transform, in order to enforce a certain smoothness on the right-hand panel. So when you go back and forth in the same kind of fashion for this kind of algorithm, what you do is you eventually reconstruct a signal that looks, so this is the time series here. You reconstruct a time series that looks an awful lot like the original signal, but it doesn't have to be the same length, and that's the key. By manipulating the STFT overlap, so the Fourier transform overlap in Windows, you can actually modify significantly the length of that signal while retaining its frequency character and its appearance. And so that's the trick. That's what I used. So down to the prize. This is an example of an ice ghost here up top. And this is its corresponding rebuilt time series that I did via this Griffin-Lim algorithm. And I will show you at last what it sounds like when you do so. So play you some excerpts. This is 9 minutes, but listen very carefully. So these red boxes are what I'll be playing here. So now we're roughly here. I'm going to skip forward to this interesting period here, which I think is about 7 minutes-ish or something. Let's see if you can identify when it drops really suddenly due to weather forcing. There's clipping there in the audio file. So you can imagine why maybe this sort of thing caused a bit of a stir. it sounds ghostly. It sounds really cool, and it's almost human, and yet not really. So it's kind of a neat phenomenology. Now we can go further with this. And so when I originally released these sounds, I got contacted by quite a few artists, and two of them decided to stick around. And there's always more that are popping up and disappearing, as it were. But these two have stuck around rather persistently. So I'll be showing you some very brief works in the last couple minutes of this talk about what they're thinking with this. So I have Sandra Volney and Lucas Cantor, and Sandra's a Canadian audiovisual artist, and she likes creating these large physical setups that are sort of sound interpretabilities. Whereas Lucas Cantor is actually a composer in LA, and he's an Emmy-winning guy, so he's quite neat and knows his stuff. But it's going into Sandra's stuff first. So her idea when she was listening to all these is that she wanted to create an audiovisual space that sort of immortalized sound in its own way. So she's created this neat process where she's created these big tanks of water, and they resonate with respect to certain frequencies that we've calculated. So you calculate the modes of a resonant tank. And we've mapped them to these ice ghosts pretty well. And so the ice ghosts make these tanks resonate. And at the same time, she's developed this neat process. Oh, this is her playing with the original ice ghost sounds with her audio software. She's a very neat person. But basically, she's created this neat process, whereby you can chemically freeze sound. So she'll excite one of these vats, these sort of tanks here, and there's a chemical process by which the actual wave patterns created by the resonances get solidified. And so she's creating a whole host of these things, distributing them in a studio room, and then playing the various ice ghosts at each station in a sort of way that you can walk through and sort of experience the entire ice shelf. So this is for the Ross ice shelf, as a function of space as you walk through it. So it's actually very, very interesting. She's got a show in March 2023 in Montreal. So should any of you be there. Lucas, on the other hand, is more on the interpretive side. So he took some of my original recordings, which were admittedly a little primitive, and he decided he was just going to mess with it and try to create some symphonies related to their feeling. So you'll hear him playing with his orchestra, and then in the background he's playing the whatever tones come out of the ice ghost. So there's a neat section around, I think, around 2 or 3 minutes, which I quite like. So he likes the dramatic feelings of things, and you can hear the ice ghost in the background. Let's see if I can find the neat little section. Let's just go from there. Quite funny. I mean, it tickles my fancy as a scientist. It's quite fun. So on occasion I'll go to LA and meet up, and we have drinks, and he shows me his music, and it's quite good. He's actually planning. So I'm currently in the process of submitting an NSF grant that will take us back to go study the actual three-dimensional physics of how these waves are actually created in the snow and ice. And he's actually planning to come with me. So he's going to write one of those NSF artist addendums. And so he wants to go play around on the ice and just get a feeling for what the environment actually is out there. So there should be some interesting arts collaborations coming out in the near future. So before I go, I'd like to plug a few other people who do this kind of stuff, and there are many, of course. So there's Doug McHale, U Chicago, does a lot of this. So he's got a lot of artist collaborations. In fact, one of whom just contacted me yesterday. In fact, so it's a relatively small community of seismologists that do it, but a lot of people who just once in a while will accelerate a signal and generate something cool. For instance, Mars quakes. This is a quick one that I found recently of what a Mars quake looks like. These signals are obviously to us are broadband, and so they sound like just this loud noisy thing. Whereas things like ice ghosts may not. That's why they're interesting to me, at least. So that's a Mars quake. This one down here is one that Rick Astor did of iceberg tremor back in the day. So I thought this was kind of cool. So this is the signal on the right here. So there's an iceberg. There you go, grinding off the coast of Ross Island. And so this is sped up seismic data from it. I thought it was rather cool sounding. Sounds a bit like whales, really. So that's what an iceberg sounds like. Yeah, aside from that, if you, to conclude this talk, I suppose, in a hit by a speeding bus kind of fashion, if you'd like to sonify your stuff, you want some algorithms and tips and tricks from what I've learned so far, then yeah, contact me. So my website's there, and my email's there. If you want to read about the actual science of the ice ghosts that we've talked about today, then there's these 4 papers that 2 of which came out this year. So yeah, please contact me. I like playing with this stuff. So with that, I will happily take any of your questions and go from there.
Thanks so much, Julien. What a fascinating presentation. I very much appreciate you sharing that with our audience today. For those of you who are tuning in, please feel free to type any questions you may have for Julien into the Q&A box. And while we're waiting on some of those to come in, I guess I had a few questions of
Sure.
my own. You mentioned that when looking at the seismogram, or I'm sorry, the spectrogram peaks, that they sometimes would move around and change after a storm. And I'm wondering if you could say a bit more about what do you think the mechanisms are that explain that? I mean, I know you just mentioned you've got an upcoming idea to look at some 3D stuff there, but without giving away too much, I guess I'd just be curious to hear your thoughts on what you think is causing that.
Oh, yes. I mean, I'm happy to have anyone else who wants to think about this. This is we actually, so there are several other groups that are actually have now decided that perhaps these aren't in fact instrument resonances, and they're gonna put in some effort. So I know that there's I was talking to a few people at the last conference I went to, which I guess wasn't Iris, it was the one before that. Anyway, but they're gonna start deploying DAS out on the ice shelf or on the ice sheets to see if we can record these things over very dense spatial distributions. The problem mainly is that it is such a complex interaction between the wind, the surface topography, the medium itself, which has all sorts of very strange back and forth parameter switches. What we think is going on, at least for part of it. So for example, there's this storm thing in the bottom left here. What we think is happening, because it has a lot of at least intuitive and also direct evidence to that effect, is that when a storm passes that does not have a depositional budget, so if it's just really strong winds, it probably will erode a bit of the surface, but not much. It'll probably, generally speaking, it won't change a lot. And so you'll get these storms that pass that do nothing. And then all of a sudden you have a storm that passes that does quite a bit. And so one of the things that I modeled numerically, or at least I tried to do some basic numerical modeling back in the day, is I tried to see what the impact would be on, if you had regular topographic features. So for example, dunes that happen at regular intervals versus a different spacing of intervals. So for example, if you imagine that the wind is coupling preferentially with certain surface structures because it's hitting dunes and not between the dunes, then you get these sort of clusters of surface sources. And so these resonances may not be true resonances from the perspective of something actually resonating and being source independent. the resonances may actually just be amplifications due to interference in the wave field. And so if you have clusters of sources that have a certain wavelength or a certain bandwidth themselves, that are distributed at certain distances preferentially that interfere with each other at a spatial locations, you might get amplifications at certain frequencies. And so that was kind of the idea. And so if you have a storm that passes through that has a big depositional budget, it might completely change the periodicity of your surface structures.
Huh.
And then what will happen is that those surface structures will slowly erode afterwards when you have a steady state wind that comes after. So you have these things at the top left here. I have a couple of these black dotted boxes that I've highlighted. Those occur after large storms. So you get a new peak pattern, and then that decays very slowly as a function of time. And that's repeatedly, right? That repeatedly happens. And so what we think is happening is that those are representative of the slow decay of newly deposited structures on the surface back to some kind of normalcy. So it's a consequence of the sort of compaction, erosion, and so on. Yeah. So it's actually quite, I mean, it's a spectacularly complicated problem. Personally, what I want to go deploy, so I'm writing this up now. I think it's got enough traction to do it because I won't even require airtime, which is the big problem. Is I want to deploy a 3-dimensional array of seismometers so we can recover wave field gradients and curls. So in other words, we want to know exactly what kind of waves are causing these things. And so that's one way to do it, is to identify directly, split the wave field, mode types. And we also want to match that with a battery of environmental sensors. So we have, we want wind shear, we want anything that related to turbulence, we want cameras out there. We're going to want, basically every possible environmental sensor you can think of so that we can directly track these things in 3D as they happen. And so that's, I think, honestly, what it's going to take. I don't think we can have anything less. So we'll have coring as well to directly determine the firn structure and so on. So it's going to be sounds like
sounds fascinating. Yeah, that's great.
Yeah, super cool stuff. Yeah.
So we did have a question coming from Esteban. He says, have you thought about cymatics, using your audio records to generate geometric patterns? I guess that's kind of similar to what you mentioned that one of the artists was doing.
Yeah, I mean, that's the thing about the audio, is that audio transpositions really are somewhat arbitrary. We're doing this for us as humans, and then we're using our brains to try to find patterns in them, right? And this goes back to, why do we find certain sounds good? Why do we find others bizarre, disturbing? And it's because, when we listen to something like these audio recordings, there's clearly information content. Because we can detect it. There's temporal changes that are not random. There's things that are happening that are, very obviously related to the real world forcing effects. The storms, there's melting, there's slow erosion. We can detect all of those by ear if we listen. So if you want to create, yes, I mean, one of the things that I'm actually, low key working on is creating a bit of a symphony of these patterns that interfere with each other through the entire array, and that turns out is kind of complicated. But it's one way of kind of, if you can identify the drift of patterns through the array, then you might be able to unlock underlying long period forcing patterns as well, which is kind of another objective. So there's a lot. Yes, I mean, yeah, constantly thinking about little details like this. But in terms of visualizing them, I mean, yeah, you're back to seismology essentially. You want to visualize wave field interference patterns. You got to go back to the original signal. The audio is more for a human appreciation in that sense, I think.
Yeah, I'm glad you phrased it that way, because it's a good segue to another point Esteban made as well about how, visualizing and sonifying these data provide a really effective way to engage the public and engage them with the science and connect them in a way that maybe they otherwise might not be able or willing to do so. So it sounds like if you mentioned there was a small group of people in the geophysics community that have done some of these sonifications and shared them. And it seems like your experience and the experience of some of these others have been largely positive in terms of the reception that's received from the general public.
Well, I think we live in our bubbles too much. We have our little set of biases. We have our little groups of people who pay attention to our work, and those who, like and appreciate and understand what we do. But by and large, most of what we do goes under the radar. It's just kind of state of affairs. So it's definitely an interesting and I think valuable effort to put forward something that can be immediately and broadly at least appreciated on some level. And you also never know what comes out of it. I mean, I'm collaborating with this Canadian artist, and she actually joined me out in El Paso for 10 days and came out to the desert with me because I have a project out there as well. And she brought her own weird little audio setup to try to do recordings, and she had this like metal plate and was bouncing little grains off of it. And as it turns out, that it provided quite a bit of insight as to the actual bandwidth of saltating grains in the desert. So I was like, okay, I have to rethink this. So sometimes the human component can actually loop around and then provide you with additional information that it's easy to forget because you're stuck in your bubble. So we're actually going to publish a little art science paper on that this fall, so it's kind of fun.
That's amazing. That's I mean, I think that's one of the things about what you presented today that I find most exciting is this collaboration that you've undertaken with some of these different types of artists. Are you aware of like how common is that? Are you aware of other artistic collaborations between geoscientists and artists? Because I can't say that I've heard that.
Well, the one that that's kind of the go-to that I think of is Doug McHale. So he's done a ton of that stuff at U Chicago. So he's had very frequent collaborations with artists. So I think he drives a student group that does projects on this. And also there's an exhibit a while ago that was sort of the travels or the slow decay of, I think it was B-15 or something, the iceberg. It was called the White Wanderer. It's cool setup. And I think he's working on something else right now too. So yeah, there are some groups that definitely do this, but we are pretty sparse. And so yeah, I think a lot of us are like, well, does an artist collaboration directly pay off, because we're all in this rat race, especially the assistant professors, and putting in a lot of time like this often doesn't seem like it has an immediate, professional reward. But I would argue the contrary. I think a lot of these things are interesting enough that, it gains you a lot of traction in terms of how your work is viewed, and that has a big component of as well. So, I think they're very worthwhile. I think it's a way to reach out, and you'll meet a lot of people in the process. And as much as many of us hate it, the art of schmoozing is like, kind of a skill that goes a bit under the radar in the science community as well. So,
that's great. Well, I think we'll have to leave it there.